view. We don't need that anymore. Let's go ahead and pop up. Oh, well, there's one. Yay. All right. So let's start off with the equations we're going to have in mind for Friday's exam. See exactly where these things are coming from, what they're all about. So exam 1 doesn't have a whole lot of equations to start with. We have 4 kinematic equations, or at least that's what I like to call them. So let's see here. We have, why does it not want to write on that? Interesting. It's seeing something that I don't want to care about. There we go, that worked. All right, so first one I start out with my position, x is equal to x naught plus v naught t plus, let's clean that up a bit, x naught, there we are, plus v naught t plus 1/2 at square. I like to call this the position formula because it gives the position as a function of time. The next one I like to talk about, I like to go with v is equal to v naught plus at. If you are in calculus, you would notice that these are that v is equal to v is a derivative of x. This I like to call it the velocity formula. And then the next one I like using a whole lot of is v square is equal to v naught square plus 2a. And then they take the difference of positions here. I like to just call it d. And for reasons which will become obvious when you get to energy conservation, I like to call this the energy formula. Energy formula there. And then there's one more that they like to give, but I hardly ever use myself. D is equal to v naught plus v on 2 t. This is basically the position formula, except instead of having an acceleration, we take the average velocity. More or less the same thing there. Let's see here. There's someone in my Zoom. Be aware that I think the whole wide world can hear you if you were to speak. And then we have weight is equal to mg. This is basically all of gravity. So we have gravity, and gravity is given to be 9.8, 0, 665, whatever. 9.8 is the general form there. A note on all these formulas here. These are all, for the time being, these are all 1D formulas. The only one that might get promoted is the energy one, because energy is weird, which should be exceedingly obvious. But all the rest of these need to be pointed in the same direction, or it doesn't work at all. So if I were to be grading this on a piece of paper, and let's see here, and it says something like, absolutely. They can come watch the Twitch. At the moment, they don't have the Zoom ID if they wanted to talk to me, but they can just absolutely come to the Twitch and chat on the Twitch chat. Let's see here. So if we have ballistic trajectory, thing comes off the top of a cliff for whatever reason. Oops. Try that again. Make it a little more square. There we go. And I think something like, there might be a question like, how far is it from here? Let me switch out my colors. Come here. And take the red one. how far is it from here to here? What is this distance here? And what a lot of people will end up doing is they'll say, right, I know what the h is, I know how far this x is because it is equal to v naught t, therefore d is equal to x plus h. And it's like, no, that's not how that works. This is going this way, and this is going this way, and those two things don't work that way. They'll sometimes do things with velocity and other stuff like that, where they end up combining orthogonal, that is a vertical with a horizontal, a vertical with a horizontal in the 1D, and the 1D equation returns an answer, but the answer is completely incorrect because they're 1D equations. They're not designed to handle multiple dimensions like that. So you have to be very careful with that. As this is given on a computer, I will not be coming around to tell you exactly why you got things wrong. But that's the thing that a lot of people end up doing. Alright, let's see here to do. R. I do not want any of the, oops, I do not need any, come here. Control A. Nope, we don't want to do that. Gotta be careful with the word. Oh, I know the problem is. There we are. Let's not delete all that. Delete, oop, that's not what I want to do either. That's terrible. Control Z that, let's fill it in. Flip that, wait, there we go. Let's go ahead and get rid of that as well. There we go. Okay, yep, sure. And then we have, I don't know, I'm not sure if forces are on this exam or not. I think certain forces aren't. But here we have some force equations. The first two, flip back there and flip it back to black. There we go. The first two we have, what are we writing on? Oh, you're writing that little square, it's not gonna work. We have that sum of forces as a vector is equal to MA, which is also a vector, which goes the first two. So this whole thing here is all about making sure that you sum of the forces and such that you have your perpendiculars with your parallels, and such that you sum only your perpendiculars with perpendiculars and sum only your parallels with parallels. So if we have some block on a slope, we can have gravity pulling, oop, you don't want to put that there. Make that arrow go down a little bit further. We have gravity coming down. F equal mg, pulling straight down. We can have a friction pulling up. Force of friction equal force, oops. It is not force, it is mu normal, and then we have a normal force. And then you need to pick your directions on this so that your parallels are with your parallels and your perpendiculars with your perpendiculars, so you end up with a, let's make a new color, come here blue, so that you only have your force, gravity, perpendicular. This comes out to be mg, and then we need a trig function. So when our theta here is 0, I need my force gravity perpendicular to be equal to mg, and the trig function which gives me 1, so that is true, when theta is equal to 0 is cosine. So cosine theta goes here, and then I have a force, force gravity parallel That's all kinds of terrible. Try that again. Force, gravity, parallel. And that comes out to be mg sine theta. And so you can sum these going this way with the parallels, and you sum these with going this with the perpendiculars, and you do all kinds of lovely things with that. And that may or may not be on this exam. And then for spring, so force kinetic friction here, we have kinetic friction. It would be the friction when our things are moving. There's also rolling friction, which works the same way as the kinetic friction, so we don't usually talk about that one. And then we have the force static, which must be the static friction is equal to the force necessary to hold the thing where it is. It's like the normal force, except instead of pointing upwards, it's pointing against the net force, the net of the rest of the forces on it, and is less than or equal to mu s times normal. And so there could be questions about when does the force static break? When does the static friction break? I believe that's more often than not a question which is not particularly often used on exams because it causes some degree of consternation, and these are generally multiple choice questions. And so the exam needs to be designed for a multiple choice examination rather than an open-ended examination, which can allow more kinds of questions. So that actually makes Dr. Ford's exams pretty good questions to be looking at for this particular setup. And then quadratic equation, I have that thing memorized, and you probably will eventually as well. Alright, is everything still rolling? Everything is still rolling. Computer appears to still be happy. Twitch says it is still happy with 3 viewers. How nice. Cool. I like it when things are working. Let's see here. How many people do I have in my Zoom channel? Where art thou, Zoom? Oh boy. Zoom got lost somewhere. Oh, no it didn't. There we are. Oop. 4 there in chat. Alright, tried going to Twitch but it kept lagging. Are there any formulas you recommend to know that aren't on there? Not particularly. Yeah. So I'm not completely entirely familiar with what has been said about what is or is not going to be on there. But I like to start. I want to start out with what was actually the equations on there, so that we have a frame of reference for what those are all about. I believe I saw something from Winhow about what was actually on there. Recitation exam review. Not to be on there. Acceleration for objects on an incline. Okay, kinetic and static frictions. Yep. Not entirely surprised. 2 bodies on different surfaces. Yeah, that is actually 2 bodies in separate surfaces is actually a very poor choice for exam questions. And springs. Not entirely unsurprised there. So I'll try to keep that in mind when I come across those questions. This here. Actually. Oh, whatever. Let me see here. To everyone. Yep, there we are. Okay, let me throw the other chat on here, so that I can at least have half a chance of seeing it before too much happens. Yeah, pointing at that one. Very good. Make it visible. Okay. Let's throw it behind my head. No. Let's throw it There we are. Let's throw it there. And throw it behind Firefox. There we go. Let's do that. All right. Now I have half a chance of seeing if anything pops up there. Oh, let's pop up the other chat. Oh, come on, Firefox. Show the pop out. Oh, come on. There we are. Minimize that. There we go. Now we can see everything. Now I have a chance of seeing everything. We'll see if we actually do or not. Okay. So if there's any particular questions that you would like to have answered, I can certainly do those. Otherwise, I am about ready to plug right into exam 1 for 2019 with no answers. All right. Have your mouse. Scroll down. All right. So vectors. You need to be careful with your vectors because you can't add them straight up. Things go weird. Just as my warning with the 1D kinematics, you need to be careful with your vectors because those 1D and 2D are not exactly equal to each other because, well, we have math reasons. The space is called Euclidean as opposed to Manhattan, and those are going to change a whole lot of things there. But so you need to go through the Pythagorean theorem if you're going to combine things. Anyhow, vector A is in the fourth quadrant. Yep, there it is. Angle 53.1 degrees counterclockwise from the minus y. Counterclockwise. Yeah, look at that, as drawn. How nice. So this is 50. Oops. Oh, right. I need to be drawing on that layer. There we go. That helps. This is 50. Ooh, let's have the black one. Let's turn to black. There we go. 53.1 degrees. All right. Real quick, like we all know about the special angles: 30 degrees, 60 degrees, 45 degrees. This one makes a lot of 1/√2s, and these makes lots of 1/2s and roots of 3/4. Oops. When you go through trig functions. 53.1 degrees and 36 point. Oops. Try that again. 36.9 degrees are also very common angles for Dr. Ford and also for anyone else who's following his exams, such as Wenhao and Vladimir. So there's a very good reason for that. These are approximately 3, 4, 5 triangles. So these are going to come up a lot, so be aware of that. So if you wanted to, if you were so inclined, you would make note that, let's see here, cosine of 53.1 degrees, sine of 36.9 degrees is equal to cosine, this here, that's the big angle, the small, that should be 3/5. And sine 53.1 degrees is equal to cosine of 36.9 degrees is equal to 4/5. So be aware that those are things, because these are very handy things to be aware. These are nice round numbers that Dr. Ford is banking on you to be aware of. And because it is a 3, 4, 5 triangle, it makes a whole lot of things very divisible because of the fifths and the 3s and the 4s. Lots of divisible things. There are lots of divisible numbers with the 3-4-5 triangle. And so Dr. Ford and the rest of the professors will keep coming back to 53.1 degrees and 36.9 degrees because of these nice round numbers. So let's see here. Where were we? Magnitude 6 meters. Wants to know the y component in this direction. All right. Let's know that bit. So we are headed down. So we can immediately strike out all the things which are positive, because it can't possibly be any of those. It's got to be shorter than the 6 meters, because that's not it there. We are 53 some odd degrees this way, so we're closer to the x than the y, so we should be looking at 3/5. Whatever the trig function is of 53.1, that would be cosine, right? No. I'll be careful here. If we're along the, let's see here. If we're along, this would be sine. This would be sine of, oops, try that again. Sine of 53.1 degrees has to be our 3/5. So we take our 3/5, multiply it by 6. That would be 18/5. 18/5, that would be 3. 15 from that, 3/5 is 0.6. Hot dog, look at that. F is the answer. Make sense? Cosine 53.1. Let's see if I did that right. Did I get that? No, I never did get the calculator to show up right, did I? Cosine 53.1. That's 4/5. Let's see here. We're out further away. Let's see if I did that right. Come here, Firefox. With the answers. Come here. Preview it. Hot dog, yep. Sine of 53.1 degrees is indeed 3/5. Yep. Okay. Where's my other chat? Come here. Oh, flippy. My computer is being unhelpful. Let's see our zoom. There we are. There's the zoom. There's the chat. There we are. 3.6 on calculator. Yep, that's what I got. All right, there we go. Now I have to bring the OBS back. Oh boy. I'm here. There we go. All right, next one. So we start a tree somewhere. Yeah, let's not do that. Control Y. Start a tree somewhere. Okay, starting a tree, we go 30 meters in the direction 36.9 degrees north of east. Okay, north of east, somewhere in the first quadrant, off this way. So this is 30 meters this way. Well, we want to go to a position which is 40 meters. Oops, let's try to get a little straighter than that. And go straight up. There we go. 40 meters that way. And wants to know the minimum distance to go this way. It wants to know this. Alright. Well, now we get into the fun parts of vectors. We need, let's see here. We will call this A. Let's not call that D. Let's call that B. Call this A. Call this C. So A plus B, these are vectors, is equal to C vector. Therefore, we are interested in B. B vector is equal to C vector minus A vector. All right, well, these are vectors, so we gotta be careful with these things. Okay. All right, so we need to do, let's see here. All right. Bx is equal to Cx minus Ax, which is just simply equal to minus Ax because C is not going in X direction either direction. So then we end up with minus 30 meters. 36.9 is here. Okay. 30 meters, and then that's cosine to the right. Cosine theta. Cosine the theta provided, which is 36.9 degrees, and then minus 30, and then there's our 3, 4, 5 triangle again. So we want the going out to the right, then we want the long one, so multiply by 4/5, and that works out to this. 30 divided by 5 is 6 times 4 is 24. 24 meters going that way. All right, we need to store that somewhere so we can do the y direction. So let's see here. Bx is equal to 24 meters. So now we do the by, and so that is, let's see here, C, that's our 40 meters going straight up, minus the AY, so there's a 30 meters sine, 30, oh, that's terrible, try again, 36.9 degrees, that one much, 40 meters, minus 30 meters. Let's see here. That was the, let's see here, sine going up, so this is the short one, this is 3/5. Let's see here, 40 minus 30, let's start with 30, 30 to 3/5, that's 6 times 3 is 18, 40 minus 18, clear that, 40 minus 18 is 22. 22 meters. So now we know that by, that's good enough, is 22 meters. So now we need our b, and so this is our Pythagorean theorem, 22 squared plus 24 squared. Well, 10 meters is not going to pull that off. 26 is bigger than both those. 32 is bigger than both those. 50. 22 plus 20. The answer has to be between 22 and between 24 and the sum of 22 and 24. So that's 46. So anything over 46 is definitely not it. Scratch those out. Can't be those. Alright, so punch that into a fancy favorite calculator. Oops. Try again. Square root. 22 squared plus 24 squared is 32 and change. 32.6 meters. Oh, look. Ta-da. Questions? Make sense? 32.6, yep. Alright. Let's see here. Last one on page 1. Vector A has magnitude of 15 meters going off that way. And direction 36.9 degrees, counterclockwise from the x-axis. How kind of him to draw that for us. Vector B has magnitude of 20 meters going straight down. Alright, if C is equal to A plus B, then what is the magnitude of C? Basically the same thing, except instead of doing this fancy business here, we could add them together. Alrighty, so let's be a little bit faster about this one. We need an AX. AX is equal to 15 meters. In the x direction, that's the cosine. Cosine 36.9 degrees. 15 meters. X, that's the 4/5. 15 divided by 5 is 3 times 4 is 12. AY, 15 meters times 3/5. 15 divided by 5 is 3 times 3 is 9 meters. And, no, try again. BY is equal to minus 20 meters. Now what's the sum? All right, we can do that. Well, this must be our CX here. That's really handy. And then our CY is equal to 20 less 9 is 11, so this is minus 11 meters, which means C is equal to the square root of 11 squared plus 9 squared. Alright, strike out anything that is between, oh, look at that. I'll bet you that it's 16.3 because it's got to be less than 11 plus 9, which is 20. It has to be more than not 11, and there's only one that fits that, and that's 16.3. Let's see if that's true. Square root 11 squared, try again, 11 squared plus 9 squared. Squared, there we are. Oh, nope. Oh, that's weird. Really? Did I do that right? I did not do that right. I did not do that right. One moment. I grabbed the wrong component. Come here. 9. Try that again. 11 plus 12. CX is 12. CY is 11. Yes. There we go. That should help. Well, you still strike out the 5. That's the right. Helps to ask the right question. If you don't ask the right question, you ain't gonna get the right answer. Yeah, hot dog. Look at that. Yep. 11 plus 12 is 23, and I believe. Yep. So I was right. I just didn't get the minimum right there. Here we go. It always helps to do the right thing. Would it be negative 29? What's negative 29? So it's 31.4 for the y component. No, the y component is minus 11. So we have by coming straight down is minus 20. And then my ay is coming up 9. So 9 minus 20 is minus 11. There we are. Yep. That makes more sense. All right. So there's our 16.3. Always helps to put them right in the right numbers there. So this one here, not that one. That is not the one we want. All right. Let me flip to the next page. Boink. Next page. Small rock is thrown up straight upwards. All right. So this is a kinematic question. We always do kinematics. Alright, a small rock is thrown straight upward at an initial velocity v0. If it takes the rock 2 seconds to reach its maximum height, what is the initial speed v0? Neglect air resistance. So we throw this rock straight up. Nope. Helps to be right on the same thing. There we go. Chuck it up straight up. We have a v0 down here, maximum height, therefore v up here is equal to 0. This is the thing you want to know about. The time of flight is equal to 2 seconds. We have no other specification about acceleration due to gravity, therefore gravity must be the normal thing here. So we had, and initial velocity, right? Final velocity, initial velocity, yep, okay. Alrighty, so we have V is equal to V naught plus AT, right? V we have, V naught we're looking for, A we have because we're on Earth, and T's we have. Yes, very good. Solve that for V naught. V naught is equal to V of 0. Shear. Oh, and gravity is pointing downwards, so minus 9.8 meters per second squared, and then T of 2 seconds. I saw something there. V final is 0 because it's reached maximum height. If it's not reached maximum height, then your V is not 0. You're either still going up or you've started to come back down, one or the other. V naught is therefore equal to this monstrosity here. So I have selected that down is negative. So this is my down. This one here is my negative for coming down, which means that my answer will come out positive. So minus times minus. Let's see here, grab that. Grab my red. This is my coming down, which means that my answer will be going up with a positive. Flip back to black. Come here. Boink. Very good. 9.8 times 2 should be 18 point something. 9.8 times 2 is 19.6. 19.6 meters time, and then we have the seconds here, cancel the seconds there. Comes out in velocities. Yay! Units work. Here we have our 19.6 meters per second. This here. A small block is released from rest on the top of a frictionless ramp. Ramp is an angle 36.9 degrees above the horizontal and length of 4 meters. 4 meters go there. Speed of the block when it reaches the bottom. Let's see if this is on the exam. Let me double check that. Come here. Acceleration for an object on an incline, not on the exam. All right. But we did the lab on this one. I'm going to go ahead and do it because we did lab on this. We got a lab. Yeah, our last lab was this problem, so I'm going to do it. Even if it's not on the exam, it was on a lab. We have the ability to do it, therefore I shall not ignore it. A small block is released from rest top of the frictionless ramp. Ramp has an angle. Here's our theta with a horizontal and a length of 4 meters as given. Speed when it reaches the bottom. All right. Well, acceleration is due to gravity in the parallel. Gravity parallel. Actually, let's go ahead and back that up. Force acceleration. Force of gravity is equal to mg, and we're going to be along this thing, so that would be when theta is equal to 0, this must be a 0, therefore we grab the sine theta is equal to ma, our m's cancel, and so we're left with an acceleration of g sine 36.9 degrees. This should be the smaller one, therefore it is 9.8 meters per second squared. And then let's see here, 3/5, right? Yeah, 3/5. There's our 3/5 front back. 9.8 times 3/5 is 5.88. 5.88 meters per second squared. Let's see here, acceleration, and we want to know speed when it gets to the bottom. We have a distance, so we grab the equation I like to call energy equation. V squared is equal to V naught squared plus 2 AD. V is the thing we're looking for. V naught is 0. Therefore, V is equal to, let's try that V again. V is equal to the square root of 2 acceleration 5.88 meters per second squared times the distance traveled, which is 4 meters. Meters times meters is meters squared per second squared. The square root of meters squared per second squared is meters per second. Hot dog, that is a velocity. Very good. Calculator, what is 2 times 5.88 times 9, times 4? The answer is 6.85. 6.85 meters per second. Close enough. Scratch out all those. The answer is there. So far, so good. All right. Is there anybody still here? Okay. Alrighty. Jake is standing at rest. Cindy runs past him at constant speed. Oh, probably more kinematics. Cindy runs past him at constant speed of 4 meters per second. At the instant Cindy passes, Jake starts to run after her with a constant acceleration of A. What is the value of A if Jake catches up to Cindy after 8 seconds? Okay. So we actually have two position equations. So we have xc is equal to, well, let's see here. Run past at 4 meters per second. All right. So we have a v naught t going to be 4 meters per second, and and then put it down to t. Jake has constant acceleration, no initial velocity, no initial position. So this is 1/2 at squared. All right. Oh, we do have a t. Oh, look at that. So 4 times 8 is 32 meters. Okay. So 8 squared is 64. Divided by 2 is 32. So this is equal to A, 32 square seconds. And these have to be equal to each other because it's asking about when they pass each other, right? So xc is equal to xj. Therefore, 32 meters is equal to A, 32 square seconds. Therefore, A is equal to 1 meter per second squared. Which that means that when Jake catches up to Cindy, he's doing 8 meters per second. Oh, good for him. Scratch out those. Put in that one there. So far, so good. So far, so good. Small rock is thrown straight up with initial velocity of 30 meters per second from the edge of roof of a 50-meter tall building. What is the speed of the rock just before it strikes the ground at the base of the building? Alrighty. So we got a building. We chuck the rock up, and then it comes down. This is, oh, we have initial speed. We have 15 meters h. So we have h is equal to 15. Oh, that's terrible, 15. Try that again. I saw something tick. 15 meters. There we go. So good. So I assume that they hardly ever use the. Yeah. None of the none of the above is not a particularly common answer, but yeah. Dr. Ford never does the none of above. If I were to do this, I would pick one question to be none of the above. But none of the above is there basically to catch any error that that was not accounted for. I suspect that most of these questions here come from the most common errors. But if I were doing this, I would do one question where the correct answer is none of the above, just to see if y'all stand by your answer. But I'm not the one. I'm not the one doing the exam, and so I believe that none of the answers are none of the above. H is 15 meters. Initial speed, Control Z, going up. Not do that. We have a V naught of 30 meters. All right. What a lot of people will do, that I do not recommend doing at all, but does work, is they'll take their V naught and they'll figure out how high the thing goes, and then from how high it goes, then they'll calculate how far and how fast it's going when it hits the ground. That can be done. I don't recommend it because the energy equation, V squared is equal to V naught squared plus 2AD has it covered because of the squares and also because it's energy conservation, which we'll get to in a few chapters. So I have the initial velocity, I have the height, I have an acceleration due to gravity. Therefore, I know that V is equal to the square root V naught squared plus 2AD. We do need to be careful with the A and D because they can, in principle, turn out to be negative. So let's see here, So, but it does work out right. So just be careful with that. So we end up with the square root. Our V naught. That's a terrible 3. Try that again. 30 meters per second squared plus 2 our gravity. If this is going up with plus, then we need our gravity minus 9.8 going down, and then our D is also going down, so we got minus 15 there. I saw that'd be right with you. Mixing that out. Put the equals there. Let's calculate what the answer is. Square root of 30 squared plus 2 times 9.8 times 9.8 times 15. My signs cancel each other. And we end up with a 34.5 or 6, close enough, meters per second. That's that question. Why is the distance 15 and not something else? Do you not need to know the maximum height for the equations to work? Not in this case, because it does work. So like I said, you could figure out, one moment. Okay. Let me go ahead and circle the answer, and then we'll get that answering that particular question. Scratch that, scratch that, scratch that, and that. There we go, 34.6. All right, so why do I not need to know what that answer is? Click on that, go ahead and, hold on a moment. Control A, fill it with white. There we go. And blank that out, you get it back, very good. All right, so give me my pencil back. Okay, now we have some proper space to be writing things on. So we can go straight up and then come straight back down like so. Yes, we could if you want to. So we have an H here and then we have a V naught here. So it goes straight up and then comes straight back down. V squared is equal to V naught squared plus 2AD. So do I need to know how it went? No, I don't. Why? Why do I not need to know how it goes? So as we, the simple answer is energy conservation. Long answer is a little longer answer. So we go up a certain amount of height, and then we'll come back down to here. This is still 0 meters. So this direction going down and this direction going up are both V. So we'll call this, let's call this one V1. Let's put this one down here, V. So V naught is equal to and minus V1. Well, what happens when I square those? V naught squared is equal to minus V1 squared, which is equal to V1 squared. Which means that when we come back to this level, we're going just as fast as we were going up. So in our particular question, I believe it was 20 meters? All right, hold on. 30 meters. So that works out, this means that this is 900 meters squared per second squared for our particular question. For both V naught squared going upwards and the V1 squared coming downwards. Could we figure it out? Sure, absolutely. But if you do that, you're putting in more steps, you're taking more time, and the more steps you put in, the more likely you are to screw something up. So in my particular experience, just grab the energy equation, call it a day, and move on, so that you have a chance to make less mistakes. All right. Yes. Precisely cancels out. Yeah. And like I said, in a future chapter, we're going to get to energy conservation, and we'll see that, oh yes, when we get back to the same height, our potential energy is the same, therefore our kinetic energy is the same. Therefore our velocity is the same. All right. We're chucking a rock somewhere. A small rock is projected from the ground with initial velocity at 20 meters per second, in direction for 53.1 degrees above the horizontal. Rock strikes a building that is a horizontal distance of 30 meters from the initial position of the rock. What speed of the rock just before it strikes the building? Okay. One moment, let me go ahead and clear this all out. Control A, delete that. Oops, nope, Control Z that. Fill it with, really? Fill it with white. There we go. Flip that background the other way. Okay, now I should be able to. It's yelling at me that I can't write on it. There we go. Yes, very good. A small rock is projected above the surface and then strikes a building. So we initial distance 30 meters. And we chuck the rock, we boink, like so. We have an angle, It wants to know the V here. We have a V naught here, Yes, very good. Okay. This is one of those cases where people can screw things up. Let's see here. So we have a Vx. We have our Ax is equal to 0. Therefore, our Vx is equal to V naught x. And so that is V naught. And then x would have to be the cosine theta. So then we have 20 meters per second. We're taking the short end of this one, yeah? Yep. We're taking the short end of this, so that's the 3/5. 20 divided by 5 is 4 times 3 is 12 meters per second. Vy. Oops, that's terrible. Let's try it again. Vy. There we go. Let's see here. So we have a Vy going up. We don't know how we're hitting the thing yet. We don't know how long it's going to take us to get there. So I think actually what we need first is we're going to need some time. We need some time to find out how long we're going to be in the air for. All right, so time. So then our position is equal to Vxt. Therefore, time is equal to x divided by Vx. Distance traveled is 30 meters. Divided by Vx, which is 12 meters per second. Meters cancel each other. Inverse seconds comes on top. That's a second. 30 divided by 12. I could do the factors on that. I don't feel like it. In fact, I don't think there are any common factors. So we're just going to end up with 2.5. No, there might be some common factors in there somewhere. 2.5 seconds. All right. So then this becomes V naught y plus gt. This is going up, g is coming down, a little more space. 20 meters per second. If this is 3/5, then this must be the 4/5. The other component of that 3, 4, 5 triangle, minus 9.8 meters per second squared times the time in the air for of 2.5 seconds, 2.5. That's a terrible 5. 5 seconds. There we go. Equal. Punch that into our calculator. 20 times 4 over 5 minus 9.8 times 2.5. We are coming down at minus 8.5. That is a very nice round number. Somebody put in some work to find that. Meters per second. All right. So a quick idiot check. Is this greater than the 20 times 4/5? I don't know. 20 divided by 5 is 4 times 4 is 16. So we had initial upwards velocity of 16 meters per second. This is less than an absolute value. So that means we haven't passed through the floor yet. So that means we haven't done something stupid. That's a good sign. 8.5 is the y component. That's not the answer. 12 is the x component. That's not the answer. The sum of those, 8.5 plus clear. There we go. 8.5 plus 12 is 20.5. So everything over 20.5 can't possibly be the answer either. Okay, so now we do our Pythagorean theorem. Square root of minus 8. That's terrible 8. Try again. 8.5 squared plus 12 squared is equal to square root 8.5 squared plus 12 squared is 14.7 stuff. 14.7 meters per second. Oh, look at that. Hot dog. Questions? Questions? No questions. All right. None yet. Alrighty. Forces. I like me some forces, especially when they act on each other like this. Two blocks, A and B, are next to each other in a horizontal frictionless surface. Yeah, good. Block A has mass of 10 kilos. Okay. You got 10 kilos here. B has mass of 15 kilos. All right, 15 kilos there. Person applies horizontal force of 50 newtons on the 10 kilogram block like so. Very good. 50 newtons goes here. As shown in the sketch, and the block moves to the right. How about that? What is the magnitude of the force of B on A? Okay. So there's a few ways. There's two ways you can go about this. There's two ways. I think there's two ways you can go about this. I'm going to show, I think I should start with the easy one. All right, so we have that our force is equal to mass, and let's start with the capital mass, meaning the two of them, acceleration as in, this is ma plus mb a. The only force being applied is our P, so that means that this is 50 newtons is equal to 25 kilograms times acceleration. Therefore, our acceleration is equal to 50 over 25 is equal to 2 meters per second squared. Therefore, our force from A to B must be equal to the mass of B times the acceleration. So that is 15 kilograms times the acceleration of 2 meters per second squared. Because this is the force required to make B move with this acceleration. And if it were not that force, then it would not possibly move. 30 newtons. Boink, boink, boink. Ta-da! That's one way to do it. That's the simple, easy way to do it. I want to know the acceleration of the whole system. Therefore, this part of the system has to also have that acceleration, and therefore the thing applying that acceleration must provide that force. That's one way to do it. There is another way to do it. It requires more space. All right. Oop. Control Z of that. That went into oblivion. All right. The second way to do it. P is applied. Control Z of that. One moment. Oh, is my Facebook blowing up? Facebook can go away, right? Yes, yes, yes. Facebook can go away. So we'll have P applied to A. Which then applies to B, and B applies back. So A. We're looking at the forces on A. We have a P going this way, and FBA goes this way. So then we have that P minus force BA is equal to its mass MA times acceleration. And then we have block B, which only has force of block A on B. And that way, therefore, force of AB is equal to MBA, like so. Okay. Well, we have that force of A on B is equal and opposite to force of B on A. So then this value can come straight into here. Right? Oh, yep. Right? Yes. So then we end up with, P is equal to MA times A plus MBA, which is exactly what I said, that MA plus MB times A. Put in the numbers and you find out that A is equal to 2 meters per second squared. And you throw it back over there, and you find out that FA on B is the, what was it? 55, that was 30 newtons. So you could go through all this rigmarole, or you could just do this simple thing here, and you get the same answer, 3 newtons. They both work. I like this one a lot easier, a lot more because it's a whole lot easier. What is the acceleration of the whole system? What is the acceleration of the little part of the system that makes the whole thing do what needs to be done? Questions about that? I see nothing. Alrighty. A block with mass m is suspended from the roof of an elevator by a light rope. Okay. When the elevator has an upward acceleration of 3 meters per second squared, the tension on the rope is 20 newtons. What is the mass m of the block? Okay. Oh. Click the right layer. There we go. No, it's not going to be. Okay. So we have a block. We have tension. It has mass. TBD. This is 20 newtons. And the acceleration is 3 meters per second squared. All right. Well, it also has gravity. mg. Okay. So T, our sum of forces, T pulling up minus mg pulling down is equal to ma. Solve for m. T, move that to the other side, divide by, move it to the other side, and we end up with m a plus g. Therefore, m, come way over here, m is equal to a plus g under t. Bunch of numbers, 20 newtons. Acceleration, a plus g, 9.8 plus 3 is 12.8 meters per second squared. And the answer is, oh, that's not it. Try that again. Let's write in all the characters. 12.8, there we go, meters per second squared, there we go. 20 divided by 12.8. 1.5656. 1.56 kilograms. Strike that, strike that, strike that, circle that. All right. If the elevator was going downwards, you would just subtract 3 from 9.8. Yes, that's correct. So if we were going down, yeah, so that's going up, right? Please tell me that it's going up. Up, yes, good. So if we were going down, then we'd have a minus sign here. That'd be probably the simplest way to do it. Or you could put a minus sign here. One of the two. So long as that minus sign gets in there, then we end up with the minus sign there, and we end up with, let's see here, that would be 9.8 minus 3, 6.8 instead. So yes. Yep, that'd be precisely the way to do it. So basically one of the things I'm showing here is that when you have, so depending on where your vectors are pointing, whether it's going up or down or left or right, pick a sign convention and stick with it through the whole problem. So you can pick up or down. You can pick, to be safe, to be consistent, not to say to be consistent. You can pick up to be always positive and down to always be negative. And then when that sign pops up the other side, you go, ah yes, this quantity at the end is pointing up or down. Or if for some reason you got a negative mass, it's like, oh, I have made an error. Something has gone poorly here. My mass should not be negative. All right. A block of 5 kilos at rest at the top of the slope ramp, 53.1 degrees above the horizontal, slides down the ramp length of 4 meters. 4 meters. Coefficient of kinetic friction is 0.2. When it is released, how long does it take for the block to reach the bottom of the incline? This is definitely not on the exam, and it wasn't on the lab, and so I'm not going to touch this one. I can do it. just not for this exam. I'll stick it at the end so I don't, and hopefully I don't forget to collect it for the next one. Yes. All right, a small rock. Projected from the top, from the roof of the top building with a speed of this much and direction of that much. What is the speed of the rock when it is at its maximum height above the ground? Okie dokie. Oh, let's click on the correct layer. This is off top, but I remember when I mentioned it. Would a scale read 0 if the elevator was going really fast when suddenly starting going downwards? It's here. Would a scale read 0 if the elevator was going really fast upwards, then suddenly started going downwards? Yes. So they kind of do that with there's this plane out there called the what's it called? The Vomit Comet, where basically where they take people, astronauts in training, people who need 0G for 3 minutes or whatever they can do, and what else? People who want to do music videos. I know there's one music video that was done on the Vomit Comet. Basically, what happens is that the plane starts going upwards, and then it basically goes into a ballistic trajectory. So we have the plane, and it follows this path. It follows a parabola with an acceleration of g, and then all the scales on the inside of this plane all of a sudden say weight is equal to 0 because everybody's falling, which is basically how general relativity was started. It was like, how do you tell the difference between falling and between falling in a gravitational field with nothing on you and sitting in the middle of nowhere space? And you can't. But yes. So so in order for that scale to actually read 0, you gotta be careful about what you're doing. So if you go upwards and you come down too quickly, your scale is going to turn negative on you. Yes. So at some point the plane has to recover, and so they do this thing, and so their acceleration being upwards with g, you end up with a g. All over here, all the scales will say 2 weights instead. So yes. Control Y that. There we go. Speed of the rock when it is at its maximum height from above the ground. Okay. So we took a rock, and it reaches its maximum height at some point. Some h here. And we have a theta here with a v naught here. And then we do the speed of the maximum height, and it wants to know v here. Okay. Well, we can go about this a long way. So we know that Vx is equal to V naught x is equal to V naught, and then let's see here, cosine theta. We'll come out of that. And then Vy, we are at maximum height. It doesn't care what that is. That must be 0. Alright. So then we have this. So then we have the 20 meters per second, and then we have the cosine of 36.9. That's pretty close to there, so it must be the 4/5 version. 4/5. 20 divided by 5 is 4 times 4 is 16. That's terrible 6. Try that again. 16 meters per second. 0, hot dog. We can do that Pythagorean. Doink, doink, doink. 16 meters per second. A rock is thrown straight up from the ground. What is the acceleration of the rock when it is at its maximum height above the ground? Okay. A is equal to minus G. Always on Earth. All right. Well, strike that. There we go. Now, not 0. That's there for that. The 0 is there for people who want to grab who go for the. We're at maximum height. 0. Our velocity is 0. Answer is 0. That was it. No, that's not it. Next one. 9.8 upwards. Gravity is always downwards. This is it here. This one is here for people who go, we're going upwards. Therefore, our acceleration must be upwards. Like, no, it's not upwards. Not that either. Our acceleration is always down and it's always 9.8. This is more or less a trick question that people get wrong because they're always rushing it. Every time. Every time they're rushing it. And every time they get it wrong. Let's see here. We have a 20 kilogram block on a horizontal surface. A force of this much is applied in that direction. If the coefficient of kinetic friction is this, what is the magnitude of the friction force of the surface exerts on block? What is the magnitude of friction force? This is asking about friction. That's not an exam, is it? Let's see here. Kinetic friction is not included on this exam. We're going to answer a different question. I think we're going to answer a different question. Let's see here. 20 kilogram block, 80 newtons. It's pulled there, 30. Coefficient, I am going to alter this question. I'm going to ask a different question that uses the same problem. So our answer is not going to be one of these here. We have no friction. This is equal to 0. I would like to know acceleration. Yep, correct. So I'm going to alter this question. Instead of asking what the magnitude of friction is on this thing, I'm going to ask what the acceleration is when there is no friction. Otherwise, we're going to keep the problem the same. Okay. I'll have kind of them. So we have the force F going upwards. I need to know this bit going here. Parallel. So this is my F. If this was 0, I would have the full thing. 30 with the 1, therefore this is the cosine. We have a force going upwards. This is force perpendicular. And this is equal to F sine theta. While we're at it, I was asked the question, what is normal force while we're at it? Because that you would also need to know that for the rest of this problem. You don't need to know the acceleration for the actual problem. You would need to know the normal force though for it. So we'll go ahead and ask that, and we'll answer that one too. So then we have weight coming down, mg, and also normal force. All right. So our acceleration. This is ma. So then our a is equal to F on m cos theta. F is 80 newtons over mass of 20 kilos times our cosine of 30 degrees. Another favorite angle, but not my favorite angle. So that is 80 divided by 20 is 4. Cosine of 30 degrees. Let me guess, a half? Nope, it's not. It's the other one. This is 3.46 meters per second to the right. And then the normal, we can do that too. So our sum of forces in the y direction is equal to 0. is equal to normal going up plus our force perpendicular going up minus our force of gravity coming down. Therefore, normal is equal to mg minus force perpendicular is equal to, where do we go? Mg is 20 kilos times 9.8 meters per second squared minus 80 newtons sine 30 degrees. And that is equal to 80 sine 30 156 newtons. And that should be up. Control Z, Z, try it again. There we go. All right. So I did a different question. I did two different questions based off this one question. I think both of these are fine for this exam. So we had an acceleration. I could find the acceleration in the y direction and the x direction. And I could also find the normal force push, making sure that this thing does not fall through the floor after the fact that is being aided by this external force here. Knowing this normal force, we could then figure out what the force of friction is, but we're not going to ask the force of friction because that's not on this exam. Questions so far? All right. Sums of forces here. Okay. Which page are we on? Page 5? 2. Okay. You have a block with a mass of 20 kilos. Each cable makes a, how nice of them, 36.9 degree angle with this horizontal ceiling as shown. Wants to know the tension T1 in the left hand cable T1, which is also going to be, because it's symmetric, also equal to T2. All right. Okay. Tension T1. Okay. Okay. So, all right, question. Do you guys want me to apply symmetries to this and make it simpler so I can fit it in space, or should I do this out the long way, just in case this was actually, say, this one was like 36.9 degrees and this one was 53.1 degrees. You guys want to do it the longer way or the shorter way? No preference. All right. Well, in that case, I'll go the short way. Okay. Let's go ahead and click on the right page. All right. So the short way. Let's try again. Short way using if I can spell symmetry, I think another M in there. All right, so we have sum of forces in the x direction is equal to T1x minus T2x is equal to 0. Due to this, T1x is equal to T2, not quite. Let me back up just half a second there. That means that T1x is equal to T2x. But because of symmetry, there we go. That's spelled right. T1 is equal to T2. So we don't actually care about this. This actually provides precisely no information here. So we want to look at, right? Pretty sure of that. So we end up looking at sum of forces in the y direction. We have that mg. Nope, we want mg. We want t1y. We end up with 2 t1y minus mg is equal to 0. Then we have that 2t1y is t1. Then we need the y component of this. Is that sine or cosine? If theta were 90 degrees, then all the t would be pulling straight up. So I want the trig function which turns 1 when you put 90 into it, which is the sine, right? Yes. Sine 90 degrees minus mg equals 0. Therefore, T1 is equal to mg divided by that there, so we end up with 2, not 90 degrees, that's not the right angle. Try that again. Back up, not 90 degrees. 36.9 degrees, there we go. Minus mg, there we are. That equals 0. Try that again. Alright, so T1 is equal to 2 sine 36.9 degrees under mg. M is 20 kilos. G is 9.8 meters per second squared. Punch that into calculator. Answer is, oh, that'd be all kinds of fun if I try to do it in my head. No thanks. 9.8 divided by, begin, 2 times sine of 36.9 degrees. Execute. Answer is 163 point, well, it doesn't matter, 163. 163 newtons. Let's try to do that in our heads for the kicks of it. So we have 20 times 10, so that's 200. 2, and then that's a sine of 36.9. That would be, let's see here. That's the 3/5 there. So then we end up with 100 times 5 is 500 divided by 3. 5 divided by 3 is 2.667. So we end up with 266. That'd be good enough to figure it out. Or 166, yeah, whatever. So that'd be 167. Doink, 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 doink. Alright. Do. Now there's a shorter version. If I'll do it the long way, I would end up figuring out what I'd have to do T1 sine, I'd end up with T1 sine theta and plus the 2 with, I would have to invoke this business over here to say that this was in fact 2 rather than doing the rest of it. Is it really? I can find that out. Let's see here. Come here. Scroll down, number 15. Nope. Nope, it's not. All right. We're getting some of the people who aren't necessarily part of my class, but that's fine. All right. A river that is 200 meters wide is flowing due east. Let's back up. Let me back up and get rid of the part that we don't need there. Okay. Yes. Doink, doink, doink. Capture that one there. All right, a river that is 200 meters wide. All right, so we have, there's a 200 meters wide. Is flowing east with a speed of 3 meters per second relative to the Earth. Very good. Boat travels across it straight north. Okay, from point A. Oh, from point A to B. If the speed of the boat relative to the river is 5 meters per second, how long does it take for the boat to cross the river? All right. So our boat is trying to go from here to here, right? But it's being carried downstream a certain distance. So that's actually going to try to go this way, such that the river will carry it down to here. So our 5 meters per second here. Okay. So taking our lovely triangle, making it a little bigger. We have 5 meters per second here. We have a 3 meters per, oops, try that again. 3 meters per second here. So then we need to know, what is this? What is our V across the river? So that would be, busting out our favorite Pythagorean theorem, we have that 5 squared is equal to 3 squared plus our Vx squared. Right? Yep. So Vx is equal to the square root of 5 squared minus 3 squared. This is greater than 0, therefore our calculators will not yell at us. And that is the square root, try again, square root of 5 squared minus 3 squared. Answer, oh, right, of course. 4 meters per second, of course it is. That's a 5, that's a 3, of course this is a 4. It's a 3, 4, 5 triangle, of course. Of course it is, all right. That makes a lot of sense there. All right, how long does it take to get across? All right, x is equal to vt. T is therefore equal to x divided by v. All right, we have 200 meters to cross. A velocity of 4 meters per second. So that is 8. Let's see here, try again. I bet there's gonna be an 8 in there. 20, no, it's not. 20 divided by 4 is 5. 0 seconds. There we go. All right. Okay. Yep. Okay. Nothing interesting there. Okay. All right. Make sure I haven't missed too much in our chats. All right. We have a block A and block B are on a horizontal frictionless surface. Block A has mass of this much, and block that MB is block this much. All right. So we have, let's see here, 4 kilos here. We have 6 kilos here. 2 blocks of light rope. Horizontal frictionless surface, F is, right? Horizontal force, 30 meters. 30 newtons. Applied block A, blocks move in the direction of F, while blocks are moving, and wants to know what T is. Alright, we're going to take this the short way. This is basically the same problem as, which one was it? Nope. This one. It's basically the same problem as this, but instead of pushing on each other, they're pulling on each other. Alright, so we have that F needs to FA, right? No, F is applied to the full force, to both blocks, mass B plus the mass of A, acceleration. Therefore, the acceleration of the whole system is 30 newtons divided by 4 kilos plus 6 kilos. Oops, try again. 6 kilos. 30 divided by 10 is 3 meters per second squared. So now we need to know the tension. That has to be just the mass of B times the acceleration. And the acceleration we have, and the mass we have, so let's see here, that's 4 kilos times the acceleration, where'd it go? Acceleration, 3 meters per second. Yet our mind is going fuzzy, isn't it? 12 newtons. Boink, boink, boink. Do. All right. Last one. Last set of questions here. A block of mass 2 kilos is initially at rest on a horizontal frictional surface. At time t equals 0, horizontal force of F is applied to the block. What is the magnitude of F if it reaches a speed of 8 meters per second after its traveled distance of 4 meters? Oh, and of course we got right on the right surface there we are. Alright, we got a block. It's got an acceleration, and it, which is not provided to us. We're told that this has a velocity of 8 meters per second, and it traveled a distance of 4 meters. Alright, so I need an acceleration. I'm going to go grab my favorite energy equation. V squared is equal to V naught squared, which is 0, times 2AD. A is what I need, therefore A is equal to V squared on 2, oops, try that 2 again. Good gravy. There are 2D. So we have 64 meters squared per second squared divided by 2 times 4 meters. And so that means our acceleration is, so 2 times 4 is 8, 16 divided by 8, 64 divided by 8 is, look at that, a nice round number, 8 meters per second squared. So now we have an acceleration, we have a mass, so now we have a force is equal to ma is equal to, let's see here, 8 times, out in the wrong order, doesn't matter, but whatever, is equal to 2 times 8 is equal to 16 newtons. 2 goes away, 8 goes away, 24 goes away. There's our 16. Nice round number. All right. An elevator moving downwards is an elevator moving downward is slowing down at a constant rate as it reaches the ground floor. All right. So we have an acceleration that is going upwards because our v is going down, is pointing down and decreasing. A woman with a weight of 150 newtons is standing on the floor of the elevator. All right. If the floor exerts an upward force of 190 newtons on the woman, what is the magnitude and direction of the acceleration of the elevator? Well, I got the upwards from all of the English, so we can immediately strike out all the downwards. Straight up. Going away. What is the magnitude and direction of the acceleration of the elevator? Well, I got a sneaky suspicion here, real quick, like 9.8 plus 2.61. I don't suppose that has anything to do with 12.9. Nope, it doesn't. Okay. All right. So let's see here. Upwards force of 150 newtons. We want to know. Okay, right. So we have a force. We have mg going this way, and we have an F going that way. This is 190 newtons, and this is 150 newtons going this way. Net force, F net is 40 newtons. We need the mass of the woman in question. Not that they would ever ask a person such a thing. M is equal to 150 newtons divided by 9.8 kilograms. 150 divided by 9.8, 15.3 kilos, right? Oh, nope. We can do our units right yet. Meters per second squared. There we go. Right. Oh, 15.3 kilograms. That sounds like a very light person to me. I don't think that's a woman. I have a sneaky suspicion that is not a woman. Real quick, like. I think that is a mischaracterization of this whole situation. 15.3 kilograms. 33.7 pounds, yeah. 33.7 pounds. That would be a young woman there. That'd be a young child. A little girl, perhaps. That is not a woman. Anyhow, I always Dr. Ford did not keep approximate numbers in mind. Anyhow, acceleration is therefore equal to our 40 newtons divided by 15.3 kilos. Our acceleration is therefore equal to 2.61 meters per second squared. Yeah, we could have done that easier. We could have cut that one out a lot easier because that has to be G. Therefore, confusion if you're doing anything wrong. This answer here, and then this one just would be going This should be the 12.9 should be the total force. Should be some kind of total of some kind or another. But that was not the thing we were going for. That should be our A. Because elevators are weird and sometimes screw them up. Let me go check the answers. Come here, answers. Scroll down. A, yep, good. Just make sure that everything was where it ought to be. Alright, last problem. Oh, look at that. I see friction here. A block of mass is initially at rest. Coefficient of friction between the block and surface is this much and that much. At time equals 0, constant force is applied to the block. While F is applied, was made to the force of friction that is being applied to the block. Friction is not on the exam. Alright, guess that's not a problem I have to do. Alright, that is all of the problems for, this is, can you see? Nope, you can't see that. So this is Ford 2019. Is there another year or a set of problems or a particular problem that somebody would like to see done? Otherwise, I can go back and make sure that I hit all the problems. I think it did. Or at least most of them. That had friction in it. Anything else? I think that's all of them, right? Yep. Yeah, it's all the problems. So, all right. Any other questions? Okay. Something went funny there. Interesting. What's in my background there? Oh, why am I background? Why am I in my background? Oh, because, oh, I know what happened. This Zoom is not pointing at chat, is it? Somewhere along the line, it got pointed somewhere else. There we go. Alright. Let's pull up the other chat. Come here, chat. Okay. Well. Alright. So. Come back here, OBS. No, you're not OBS. Alright. Well, in that particular case, I will go ahead and do the rest of these friction problems for the next exam, so that I don't have to do them later. Okay, come here. All right, I'm gonna do the rest of these friction problems so that I can direct people to those later, and then I'm gonna call that the stream. So I got 3 friction problems left. All right, block of mass 10 kilos is initially at rest. We have frictions. We have it's horizontal surface, very good. T force, horizontal force is being applied. Okay, so we need to find out what our friction is. So we have our block. We have mg pulling down, therefore we have a normal pulling up, which is also equal to mg. So that is 10 kilograms times 9.8 meters per second squared. And so that is 98 newtons. We have a force going this way of 25 newtons. And a force going this way, which is friction, is equal to mu in. All right, so the first thing we need to do, we can find out if our static friction breaks or not. So force friction static is less than or equal to 0.4 times 98 newtons. 0.4, there we go. And that is 9.8 times 0.4, 3.92. 3.92 newtons, which is less than the 25 newtons being applied to us, so this breaks. So that's not it. So when F is applied, it was the magnitude of the force of friction. Therefore, we are under the kinetic friction, which is mu k normal, is equal to 0.2 times 98 newtons, which is half that, 1.96 newtons. Uh-oh. Oh, there we are. I know what the problem is. God, move the decimal around. Silly me. This actually goes here. Okay, so I actually went too far on that. That goes there. That's not relevant though. So our force of friction static is less than or equal to 39.2 newtons. There we are. Now that we got the math right, that always helps. All right, well, if we're under static, that means that nothing's moving. And in order to make sure nothing is moving, our force as friction static has to be equal to 25 newtons, and nothing moves. Nothing, whatever, moves. Scratch that, scratch that, scratch that. Our friction is 25 newtons. Alright, scroll up, find the last friction problem. Not that. There we are. Here's a friction problem. Okay, we got a block, it's going down. We have an angle. We have a distance traveled. We have a kinetic friction. So we have, let's click on the right thing. We have a block. We have force, gravity, parallel. We have force, friction. We have normal. We have force, gravity, perpendicular. Alright. So let's start out with this one here. We have mg and then the cosine. Oh, I need more space. Anyways, mg, yeah, cosine theta. Right, above that, yep. Go ahead and punch that in the calculator. We have 9.8, cosine 53.1. That is 29.4 newtons. Which means that this is also equal to 29.4 newtons. This bit here has to be mg sine theta. Punch that in the calculator. 39.2 newtons. This is 1/5 of normal. Delete that. So this is 5.88 newtons. So that means that our total force, F parallel, is equal to 39.2 minus 5.88, 33.3 newtons. Yep. Acceleration is equal to force parallel over m is equal to, divide that by 5, 6.6 6 meters per second squared. So we have an acceleration. It's here. From when it's released, how long does it take to reach bottom? So I want to say time. Okay. So then we have that x is equal to 1/2 at squared. Therefore, t is equal to the square root of, let's see here, 2x on a. Punch our numbers in. Square root of 2 times 4, divide by 6.66 whatevers. Answer 1.096 seconds. Here we are. 1.10 seconds. Okay. I believe there was another friction problem in here that I didn't get to. Clear that out. So there's another one. It might have been the one I altered. Where'd it go? Not that one. Not that one. This one. This is the one that I altered. Okay. Okay. So we have the normal forces what we needed here. We're going to apply. All right. So a 20 kilogram block moves on horizontal surface. We have a force going up and to the right of 80 newtons, direction of 30 degrees above the horizontal. If the coefficient of kinetic friction between the block and the surface is 0.2, what is the magnitude of the force of friction? Oh, right, we're almost there. So let me go ahead and grab stuff, get rid of stuff. So we have a force normal on this already. That's really handy. Don't care about the acceleration. Delete all that. What? Oh, flip it, really? Control Z. Flip that. Fill it in. There we go. All right. So I have my force normal already from when I went through this problem the first time. But now I need, nope, not that one, this one. There we go. So now I need my I forgot to turn my colors back. There we go. Force friction is equal to mu force normal. I have my force normal, 156 newtons, times my 0.2. 156 times 0.2 is 31.2 newtons. Hot dog, look at that. The answer is present and accounted for. All right, that's all the friction problems at the end. I don't think I have anyone else. I said until 10 o'clock. That's 3 minutes from now, 2 minutes from now. So I have done what I said I would do. Good night. I will see my students who are still in stream for whatever reason on Friday, if they are in the course I am proctoring on Friday, and everyone else in exam and labs next week. All right.